we introduced these basic operations, and we try to use this operation to describe some problems and, as we'll see, solve some kind of problems by using the properties of this object, of these mathematical objects. Okay. Okay, so we have seen the basic operations and a very important quantity which can be computed for the square matrices, which is the determinant. I didn't give you the exact rule for the computation of determinant, unless the very simple cases of matrices of order 2 and 3. You must know that, so you will see that there are very powerful algorithms or numerical functions, numerical methods for the computation, which translate into functions in Python, for example, for the computation of this quantity for very large matrices, for matrices, for every matrix. So we don't care. We don't care about the way in which the determinant is computed, but we'll see how this is important for some problems. So it's important to compute it, and we will do it numerically, unless if you want to do calculation pen and papers for matrices of order 2 and 3, like the examples that I will show you during this lecture. Okay, I want to recall some basic definitions, since sometimes I will talk about some special matrices, and so it's a good thing to renew to recall some definitions. These are just names, but they correspond to some special structure that we have in mind. Okay, so. An important class of matrices are the square matrices. Square matrices are the matrices in which the number of rows is equal to the number of columns, so they are called a square. Okay, even if from a graphical point of view they don't appear exactly as a square, but the idea is the same. So same number of rows and same number of columns. The determinant is a number that can be computed for any square matrix. Okay? The determinant can be computed only for square matrices. Okay? It's defined only for this one. Other kind of matrices which are important in the set of square matrices are the diagonal matrices. Diagonal matrices are the matrices in which the numbers, the entries, the elements outside the main diagonal are 0. I didn't stress this point too much in the past lectures, but I'll try to convince you that this is okay. These notations, well, this is just a picture, right? Means that these are numbers. I don't want to write the letters, symbols, and anymore. This is a square. Is a square 4 by 4 matrix. Starts means well, these are numbers. Okay, every number you have in mind. So this set, the numbers which are in this position in the matrix are called the diagonal, the main diagonal of the matrix. Okay? This is the main diagonal. This means that the elements are the elements in which the two indexes are equal. A11, A22, A33, A44, in this case A55, and so on and so forth. Okay? This is a diagonal matrix. No, sorry, this is the main diagonal of a matrix. Okay? A diagonal matrix is a matrix in which all the elements in the matrix are 0 except the ones in the main diagonal. Okay? These are zeros, and the numbers in the main diagonal are different from 0. Okay? This is called the diagonal matrix. Okay? I want to stress these names since these matrices that I will show you, this one and the next one, have these matrices have these special structures, and for these matrices some calculation is very easy to do. Okay, nothing to compute essentially. Okay, this is a diagonal matrix. Okay, suppose that you have a matrix made up in this way. These are numbers, whatever number you want. Okay. Okay. This is called an upper triangular matrix. Okay. Upper triangular means that all the elements below the main diagonal are 0. Okay, this is upper triangular matrix, and you can imagine what is a lower diagonal matrix. I don't. This is the upper. This is upper triangular. I may define equally as well a lower triangular matrix, the matrix in which all the elements which are above the main diagonal are zeros. Okay, so just the. Okay, this is the name. So we have diagonal matrices, upper and lower triangular matrices. And full matrices, triangular, with you. Okay, so okay, so. I want to remember that for the another matrix which is very important is the identity matrix, which is a diagonal matrix in which the elements on the diagonal are equal to 1. This is a special matrix, okay, which is called identity. This is another matrix which having a name. And no, the other side. Okay, these are the main properties of the determinant of a matrix, and remember that for triangular matrices or for diagonal matrices, the determinant is simply calculated by doing the product of the elements on the main diagonal. Okay? So if in the main diagonal there is a 0 for a diagonal or a triangular matrix, the determinant is 0. Okay? This is quite easy. Okay? So for this kind of matrices, the determinant it is very easy to compute. Nothing to do, just one multiplication. The multiplication of all the elements in the diagonal. This is important since some exercises, some cases, some problems are written in this way. If you recognize a triangular or diagonal structure, then the computation is typically quite easy. Okay. Okay. So now we have to introduce another idea, another definition, if you want, which is a bit more complex. And finally, we need to introduce another characteristic of matrices, which is called the rank of a matrix. With these two new properties and definitions, we will be able to start the main topic in linear algebra. So our main interest in this set of for these slides, for this part of the course, which is the problem of solving a linear system. Okay, this is the first main topic that we consider. In order to do this, we need the notion of rank. And the rank is defined through the notion of linear dependence. Okay, this is a bit subtle definition, but I'll try to show you. So, suppose to start with a set of vectors. Okay, we start, in this case, we have m vectors in Rn, means that all the vectors have n components, n elements, okay, of vectors of dimension n. So they have n entries, okay? Okay, so we can compute, this is on the left of the equal, is a linear combination of these vectors, okay? So this means that we multiply every vector by a number, which is a scalar. Look at the notation. The alpha 1, alpha 2, alpha m are scalars, so are numbers, real numbers. I multiply every vector by a number. These numbers can be different, so alpha 1 v1 is another vector, alpha 2 v2 is another vector, and then I sum up all the components. I do the summation of this linear of these vectors, scaled vectors. Okay. In the slide before, okay, something like this. Well, this is a linear combination with two vectors. Okay, we generalize this computation to every number of vectors. Okay, so suppose that you are able to do this. Okay, this is a linear combination. Okay, then we say, this is the definition, is a property for the set of m vectors. So it's a property which is related to the vectors v1, v2, vm. So these vectors are said linearly independent if their linear combination is 0 only if the alpha, the coefficients alpha 1, alpha 2, alpha m are 0. So their sum, their linear combination can be 0 only if the parameters alpha 1, alpha 2, alpha m are 0. Okay? What does it mean? If, on the contrary, conversely, if you have that this linear combination is 0 and sum of the coefficients, the scalars alpha I are not 0, then the vectors are said linearly dependent. I want to stress, so this is the definition of linear dependence or independence, which is not independent. When they are not independent, they are dependent. So vectors can be or dependent or independent. Okay? No other possible situations. Okay? I want to stress, maybe if you studied a bit of probability and statistics, you know, you have in mind a notion of dependence or independence between random variables and so on and so forth. Nothing to do with this one. The name is the same, dependence or independence, but this is a geometrical or algebraic condition, property. Okay? Is a definition which is valid for vectors in a given set. Okay? So nothing to do with the dependence or independence of random variables. I want to stress this point since we will see in the future lectures the notion of stochastic dependence or stochastic independence. But this has nothing to do with this one. So unfortunately, the name is the same. Dependence and independence. I want to show you what does it mean dependent or independent for the vectors in these settings. So in the setting of linear algebra. Just with an example. Then I'll try to do maybe to describe this notion in a geometrical way. So by doing some graphs. Okay, so from an algebraic point of view, look at this situation. So we have three vectors, v1, v2, v3. These are three vectors in R3. So they have three components. Each of the vectors have three components. So n is equal to 3. So they live in R3. This is our framework. And they are three vectors. Okay, these vectors, I say that these vectors are dependent. Okay, why they are dependent? Since there exists a linear combination of these vectors such that their linear combination, their sum is 0. Let us compute this. So this is exactly the linear combination of these three vectors. So it is a linear combination in which I take twice the vector v1. So twice means I multiply by 2 the elements of the vector v1. So this is 2, 0, 4. Okay? 2v1 is 2, 0, 4. Okay? V2 is V2. Minus V3, so this means that V3 is multiplied by minus 1. So look at this linear combination element by element. When we do the sum of vectors, we do the sum element by element. So the first element of this linear combination is twice V1, so 2. 2 by 1, 2. Plus 0 minus 2. What is the result? 0. So this is 0. Then second element, 2 times 0, 0. 1 minus 1, 0. And we get the 0. Okay? Third element, 4. 2 by 2. 4 plus 1, 5, minus 5, 0. So I found for these three vectors a linear combination. Linear combination since I take a vector and multiply by a scalar, then I take the other vector and multiply by another scalar, and so on and so forth, and then I sum. Okay? So this is a linear combination of the three vectors giving 0. But what does it mean? Well, we may write this equation, which is no more equation, it's a property for the three vectors, in this way. So V3 is equal to 2V1 plus V2. Simply take V3 on the other side of the equality. Okay? These equalities are equalities component by component. So there are three summation. Okay? One for each component of the vector. Okay? So how can we interpret this result? This is an algebraic result. I found a linear combination of these three vectors such that the linear combination is made up by coefficients which are not 0. These alpha are not 0. 2, 1, and minus 1 are these numbers, alpha 1, alpha 2, alpha 3. Okay? This linear combination gives me 0. So V3 can be expressed as a linear combination of V1 and V2. And this is the reason why we call dependent these three vectors. Dependent means that one or more than one vector, in this case one vector between these three, can be expressed in terms of the other ones. Okay? As a linear combination of the other one. So what does it mean? It means that if I know the vectors V1 and V2, I can obtain the vector V3. So the knowledge of V1 and V2 is sufficient to, and the parameter alpha 1, alpha 2, and alpha 3 is sufficient to give me the vector V3. And so I say that they are dependent. Since V3, in this case V3, depends on the other two. Okay? Okay, so this idea of linear dependence is quite important. I try to give a picture, to give a graph, just to convince you about this. Well, I want to stress this point. We didn't do any exercises for the, well, not exactly. The important thing for this definition is that you try to understand the meaning of this idea. So, if you have a set of vectors, they are dependent if one or more than one of these vectors can be expressed as a linear combination of the other ones. This is the message. Okay? If this is not possible, then we say that the vectors are independent. Okay? Okay, so take some vectors in R2. Okay, I try to make some plots, some graphs. Okay, I try to translate the vectors into geometrical objects. Okay, so don't worry if you really don't know more. Well, it's not really geometry, but you have to know in this case what is a plan, a Cartesian plan. Okay. So you know that we can describe R2, the plan, with a set of coordinates, the x-axis and the y-axis. Okay, right? You follow me? Okay. And then, as I told you last time, if I take a point here, okay, I can take the coordinates of this point. This is x1, this is a point in the plan, this is x2, and this is the vector v with component x1, x2, which I draw in this way. Okay? So you can identify vectors with two components in a graphical way by looking at this geometrical object. Okay? Just a line arrow starting from the origin up to that point. From the origin to the point, the coordinate of that point are the component of the vectors, of the vector of that vector. Okay, this is the geometrical description of a vector. Okay, this is why vectors generally can be represented in and they represent some geometrical object. Okay, this is the projection, so it's something more striped. Okay, you know this angle should be 90 degrees. Okay, is the projection on the axis. Okay, so suppose that I have another vector. Okay, I'm trying to do the picture, but I'm not so good painter. But anyway, I try. Okay, suppose to have another vector. This is V. We call V1. V1. This is very. It's not a good notation. V1. Okay. Let us take another vector, something like this. Okay. This is component. Just give me this. I call this Y. It's better. Y component. Sorry, and X component. This is Y1. Y1. Okay. This is the x-axis, and this one is the y-axis. So 1 is the number of the vector, and the vector has component x1 and y1. It's more convenient. Then I this is y2, and this is x2. Okay, so I have the vector v2 equal to x2 y2. Okay. Okay, so you know what is the graphical rule for the computation of the sum of these two vectors? Parallelogram. Yes, the parallelogram rule. So if you want to compute the sum of these two vectors, you can apply this rule. This is a geometrical rule. I have to. Okay. So you have to plot the parallel lines of the vector. So I apply here the vector. This should be parallel to this one. More or less, okay. Then I apply here the vector parallel to V2. And then I take as a result the sum, which is something like this. This is V equal to V1 plus V2. Okay? parallelogram, which it's not really a parallelogram. This should be parallel to this one with the same length. This should be parallel to this one. And then you take the diagonal. Okay? Okay. So, think about this situation in this way. The vector v, the vector v, the vector v, v1 and v2 are dependent or independent? They are dependent. Why? Since there is a combination of v1 and v2 such that we can obtain v3. We can write this condition by saying that v1 plus v2 minus v is equal to 0. So I'm writing a linear combination of the three vectors which gives me 0, the 0 vector. Okay? Okay, so linear combination and dependence essentially mean that in this case, in this situation, we can express the vector, the purple vector, the vector v, as a combination of the other two. So, in principle, I need only v1 and v2 for knowing any other vector v of this kind. Okay? Okay. What is the property of the vector v1 and v2? The property of these vectors, this is v1 and this is v2. I try to do another picture. Okay? This is more difficult. This is v1, this is v2. Okay, these are two vectors. Okay, my sentence is that any other vectors in this set, so in R2, can be expressed as a linear combination of these two, v1 and v2. Any other vector. Okay, so let us take another vector, like this one. Okay? I do this geometric transformation. So, first idea, what does it mean from a graphical point of view, the multiplication of a scalar for a vector? So what is the effect of, given a vector, v1, what is the effect of multiplying it by a scalar? Not translation. No. You take the same line but a vector with different length. So if you multiply it by 2, you are doubling the vector but remain in the same direction. Okay? Since the components are doubled, but the direction is the same. Okay? If you multiply a vector by, for example, 1/2, you are taking the vector which is in the same direction but having half of the length. Okay? What does it mean when you multiply a vector by a negative number? you change the direction. Okay? So if I multiply this vector by -1, okay, I'm taking the same vector, the vector on the same line, but in the other direction. Okay? So multiplying by a scalar means change the length of the vector, but remain in the same direction, positive or negative direction. Okay? Stop me if you don't understand this. These are only ideas. Okay? All this can be proved by writing formulas, by doing calculations, but not so. The most difficult things that you have to know for managing this situation is the Pythagorean theorem, just for the computation of the length. Okay? Okay, so my sentence is that if I take one vector, a third vector in this situation, this third vector can be always expressed as a linear combination of v1 and v2. Okay? The idea is to do this projection. Okay? I take this vector here. Let us draw this in ink. Then I project this one. No. Oh, I must have a 90 degree here, 90 degree here. Anyway. I'll take this other vector here, okay, this pink vector. So the purple vectors are the original vectors multiplied by a scalar. Okay, so the pink vectors are 1/2 v1 and 1/3 v2. No, 2/3 v2. Okay, you follow me? The purple vectors are simply a scaled version of v1 and v2. So they are 2/3 v2 and 1/2 v1. Okay? But then the red vector is simple. The red vector, we call red. I call it red. So red vector. What I'm saying is that V is equal to 2/3 V2 plus 1/2 V1. Okay? 2/3 and 1/2, okay, the rule of thumb. I'm looking at the picture, but we can do the calculation exactly. Okay? And this means that I'm writing a linear combination, V1, just to put it in order, 2/3 V2 minus V equal to 0. Okay, so this is a linear combination with coefficient different from 0, giving me the vector 0. So these three vectors are dependent. Okay? Okay, so this means essentially that if you generalize this construction in R2, that if you have two vectors like this one, V1 and V2, you can write any other vector in R2 in the plan, simply as a linear combination of these two. So these two vectors are very important since they can give you the possibility of writing any other vector. And these are called the bases for this space. But we will not enter in these details. But the fact is that V1 and V2 are independent. Okay? They are independent. It can be proven by pen and paper that they are independent. Any other vector that you add in this situation makes you a set of dependent vectors. Okay? So V1 and V2, which are independent, are very important. Since by knowing V1 and V2, you can write any other vector in this set. Okay? So the independent vectors are really very important in many applications. It would be nice to draw a picture to extend this situation to R3, but really I'm not able to draw this kind of pictures in 3 dimensions. But in 3 dimensions, you can imagine that if you know 3 vectors, you can describe all other vectors in the space. And if you have 2 independent vectors, you can describe all the vectors which lie in a plan inside R3, the 3-dimensional space. And these are the typical reasoning that you do when you work with linear algebra, with linear geometry, and you'll see that this kind of reasoning is very important in the applications. For example, when you will study linear regression, multivariate linear regression. Okay? This is very important, since the multivariate linear regression is a linear combination of some vectors, essentially. So the mathematics is the mathematics of linear combination. Okay, so I can give you now okay. So we can define. Oh, here is the title of the slides, which does not appear, but I don't know why. Anyway, this is the definition of rank. So the rank is a number which can be which characterizes any matrix with any dimension. Okay. So while the determinant can be computed only for square matrices, the rank can be computed for every matrix. Okay? What is the definition? So with this definition, you can understand why I insisted on the notion of linear independence, dependence and independence. So when you have a matrix A is whatever. Whatever matrix you can write, so rectangular or whatever you want. Then the rank is the maximum number of rows or columns which are linearly independent. Okay, this is the definition. So with this definition, we can say immediately 3 properties. 3 properties, essentially. I want to stress that we will not compute the rank of any matrix by pen and paper, just only some examples. I'll give you only an example, which is the last sentence here in the slide. But luckily enough, there is a Python command for the computation of a rank of any matrix. It's linalg.rank command. NumPy linalg.rank. Okay, you'll see this. You'll see this. Okay, so first thing that we have to stress by looking at the definition. The rank is an integer number. Is the maximum number of rows or columns which are independent. Well, I want to stress that you look at the matrix as a set of vectors. So take a matrix. you can look at the columns, and the columns are vectors, okay? Right? You follow me? Vectors, and then you apply the notion of dependence or independence for that vectors. Or you look at the rows. The rows are vectors, and then you can ask if the rows of the matrix are linearly dependent or independent. Okay? Matrix or rows is the same. Okay, so the rank is an integer, a positive integer. It can be 0 only for the zero matrix. Zero matrix is the matrix with all the zeros as elements. Okay? In that case, the rank is 0 by definition. You have to define the starting point. Then is an integer, so it can take values 1, 2, 3, 4, 5, up to what? Since it's the maximum number of rows or columns, then the maximum value is the minimum between the number of rows and the number of columns. Well, this is a game, but suppose that you have a 3 by 4 matrix. Okay? Since you are looking at the independence of the rows or the columns, you have 4, this is a 3 by 4, you have 4 columns and 3 rows. So the rank can be at most 3, since 3 are the vectors that can be independent. Okay? No more. So the rank is less than or equal to the smallest dimension of the matrix. So a matrix with 2 rows and 100 columns can have at most rank 2. Okay? This is important. Not 2 or 100. It's important that the rank is the minimum number, the minimum dimension of the matrix. Since, as we'll see in the few slides forward, that this rank is the key quantity for characterizing the solution of linear systems. Of a linear system is the key quantity. It's the quantity that we have to look at for deciding if a linear system has or not a solution. So, one very important situation, again important for the problem of solving a linear system, is that there is a link between rank and determinant. The determinant is any real number, so the determinant can be positive, negative, real number, whatever. The rank is an integer, a positive integer, 0, 1, 2, 3, 4, up to n, or n. Okay? But what is the relation? So look at the case of a square matrix where the determinant are defined, only square matrices. Okay, so it can be proved that if the determinant of the square matrix is different from 0, so the determinant of the square matrix is different from 0 if and only if the rank is maximum, so is n. Okay? And this is one possible way to compute the rank of a matrix, square matrix. You take the determinant. If the determinant is different from 0, then rank is n. Okay, this is one possible way. Okay, this is an important property. I want to say that, but you will not do this kind of calculation, that for the computation of the rank pen and paper, well, it's very boring exercise. You have to look at, take a matrix take the all or the largest square matrix inside the given matrix. Okay, so for example, suppose that you have a matrix with 3 rows and 5 columns. Then you can look at all the sub-matrices 3 by 3. Okay? They are not. They are 1, 2, 3, they are 5. Okay, no, more than 5. Okay? Okay? Then for each of these sub-matrices, you compute the determinant. If one of this determinant is different from 0, then the rank of the original matrix is 3. If all the determinants are 0, then the rank is not 3. So if the rank is not 3, it can be 2. And so if you want to say that the rank is 2, you have to look at all the sub-matrices of your matrix of order 2. Square matrices of order 2. All the possible sub-matrices 2 by 2. Then you compute all the determinants of these sub-matrices. If there is one of this which is not 0, then the rank is 2. You know that, well, it's the probability of doing an error during this calculation is very, very high. Really very, very high. The luckiest situation is the situation in which you find the submatrix and the determinant of that submatrix is different from 0. And so you immediately say that the rank is 3 in this case. But if all are 0, and if you didn't do any error, and you are sure that all are 0, then you have to compute all the submatrices of order 2. Oh, it's really boring. Okay? But luckily enough, we have a very powerful algorithms, Python, for example, which you will download the package for doing this calculation, which is NumPy. Inside NumPy, have you tried NumPy? No? You will download NumPy Friday, next lecture. And then inside the NumPy, there is a package for doing all the linear algebra calculation, which is linalg. So you will download the toolbox, the library, and the command is numpy.linalg.rank, and you will get the rank of an array, of an matrix. Okay? Okay. So I think that we can have a break. Okay, 10 minutes of break, and then we continue with the introduction to linear systems.
Per fortuna fa una pausa. Sì, no, ma andiamo a dire l'ora di cos'è, che capace dobbiamo fare. Ma in realtà che serve. No, neanche provate a dare battete dello computer. No, l'altra volta no, sempre indecisi. Diciamo poi. Anche da arrivare a chiedere. Si va a chiedere o no? Andiamo a vedere. Te le preso, no? A me questo non lo prende. Dovete aggiornare. Bravo, no. Perché io prima non me l'ha fatta prendere, addirittura mi diceva tipo alle 2, cioè il tempo era scaduto. A me ieri. E provate ad aggiornare l'app. Bravo. Io ho aggiornato l'app, faccio l'aggiornamento. Ah sì, per la presenza. Ah sì? Sì. Vabbè, allora per questo noi lo andiamo a dire. Oppure tipo quella di prima non l'ho presa. Cosa stai in giro con una bottiglia di olio che siamo in giro sopra? Vedi quella roba lì? Esatto. Era strano. A me mi dava proprio la...
No, a me ora mi dà assenza, io l'ho aggiornato.
A me prima me l'ha fatta prendere dopo mezz'ora, però poi mi ha dato assenza. Quindi magari te la dà, però poi te la toglie.
Non vedere così.
No, anche io.
Pure te lo
l'ho ricordato, l'ha presa sempre.
vedi.
These vectors in R2, these are 1, 2, 3, and these are vectors in R2, like the one that we loaded. Yeah. Or go like the linear. You can try. Okay.
No, le mando domani.
The other interpretation is that you will do
Scusa, non teoria potrebbe.
Ma poi lui non ha parlato
you need the three coordinates.
L'ho detto pure le prime volte, a me mi frega.
No, quello non c'era prima, però
Infatti è vero che nessuno voleva fare.
forse infatti no, adesso io non c'è no, io poi io li mo li chiedo dai
dimension 3 that exists one submatrix of dimension 3 having determinant different.
Okay, I see. One question, actually. We have three matrix.
So, if the determinant is different from 0, then the dimension is 3.
Okay.
Is the determinant
Lorenzo ha proposto il derby in sabato domenica.
0 più 3, right?
Cioè il derby è così mezza domenica
if the determinant
che sarà al 0
then the rank can be
ha detto che doveva fare A
Come to by you have to.
yeah, you have to find
infatti lui mi ha detto al lavoro poi dopo
having determinant different from 0.
Here comes my question. So you're finding that matrix, like it's not only this one, like the or just 2 by 2. So if it's only 4, say 1, 3, 7.
Però sono gentilissimi. Ci hai parlato? Sì. Sono proprio super gentili.
Poi un terzo dell'aula.
Sono gentilissimi, per forza.
Tipo 21.
21. Però ti posso dire, all'inizio mi sembrava di più. All'inizio mi sembrava di più.
No, perché magari alcuni sono nel gruppo B forse. Però per essere cioè sono tipo un terzo.
Ma perché questi fanno il double di più. Poi sai, una teoria è che magari negli Stati Uniti non li fanno più andare. Perché poi non ce l'ho mai sentito. Sai che c'era più spesso? Tipo gli altri anni.
Sì? E allora...
E adesso sicuro che sono per quello magari. Oddio, non lo so.
Cinesi non c'era prima, non c'erano così tanti.
No, mai visti così tanti.
Ma chissà se tipo... Chissà se sono tipo loro che decidono di venire qua, tipo solo il governo che dice capito?
Per sparpagliarli un po', capire un po'.
Io ti parlerò per resistere, feci un corso. Tipo a lezione eravamo noi normali, io ero una volta di cinesi grandi, tipo di 40 anni, 50 anni. Io parlavo di qualcuno così, tipo lavoravo in una banca. E il governo aveva una capito? Cioè,
Vabbè, poi San Gallen ci sta.
Andavamo andati perché erano tipo banche, poi tipo le aziende sono il governo, così tipo per banca importante.
Abbiamo visto molto.
Vedi? Così tipo per una banca del governo avevamo andati lì, capito?
Cioè, ha work ethic.
Lavoro un botto. Non hai iniziato di fare.
No, try to No, I thought I signed up, but I have
No, yeah, like it's absent. I have absent.
Yeah, I have to, but try to update the app. Like it was working with like the previous.
Yeah, but this is normal because like after 15 minutes it closes. I just forgot, I think, to do it within time. So yeah, well, actually, thanks for reminding me. I forgot.
I don't know if someone has a lot of sense on it.
Yeah, but I lose 1 of 4 chances to release actually.
No, andrebbe dimostrato, sono due vettori generici, andrebbe dimostrato due vettori che
Yeah, because I think there are
su Python, se su Python.
Quindi sono e poi avevo scritto due cose importanti. Questi vettori
something changes. I'm not almost sure. Let's just ask him. Better safe than sorry.
io le do 1 e V2 e poi mi prendo un qualsiasi altro V, questi tre vettori sono sempre dipendenti, sempre, a meno che non siano allineati, però se sono allineati sono proprio dipendenti.
va bene questo.
Professore, una domanda un po' meno sofisticata. Le presenze.
Ah, sì.
Non ce l'ha fatta prendere.
No, vabbè, non vi preoccupate.
Se mandare l'email, cosa così?
Consider that if you send me an email, I don't know you, so you can send me an email even if you are in the United States. Yeah. So your colleague says, okay, I did this lecture. Send me an email to. I cannot check if you, even if we design on a sheet.
Yeah, sono qui.
That's a fair point.
Yeah, you can sign for your colleague even if he's not, even if he is not here. So it's useless. So for this period, for these weeks, I hope that the IT service will fix this bug.
There are no uncompliant policies in this course.
There is, but it's something.
It's up to you.
I have to.
Okay,
You are attending.
like you don't know us, like you see the name, but you don't know who.
Maybe you see like a drop.
Yeah, but you
the
see
number
like
of
the
attendance.
record.
Yeah.
Then you can
Yeah. So I'm
Like if nobody shows
I'm waiting that the IT service will give us a very knowledge this up, and if they will do this during the next week, okay. Otherwise we will see. I'll see by eyes. And look, if you are half of the first lecture, then I started to be worried.
It's just like in case I have to go back, I don't know, to my country or something happens. I'm losing one of those classes to be. Like I'm not planning to be absent, right? But Spain. No, because Spanish. Why Spanish? Because I'm troppo caldo.
Yeah, that's completely wasted. It's easy to study that. I had it in bachelor's and studio probably too, and in high school, so. And he's doing like the real basics, and not even like if you don't know how to calculate it. I think it's not really the important part. Yeah, if you're going to do
In Germany, you had like 2 hours like taking slide like that, and then you had training for how to calculate it, and no one went to the
Ma non gradino, che sta poi da io ho giocato Monte Spartato, sai? Che categoria? Ho fatto regionali, nazionali, ho vinto quello dilettantissimo, no? Però lo fa da anni ed è con Monte Spartato, tutto bene, che sta in 10 anni è molto difficile. Però nazionale campionato. Siamo fatti i finali di... Non succede è spinta però. Corre, io sono prima guarda. Abbiamo messo un gruppo del canale B, siamo andati a giocare a Bologna. Io pure a noi c'avevamo un gruppo. A Roma vabbè, se poi trattavano da chi del numero
Raga, io l'ho reclutati 5-6 già, quindi qua famo calciotto mi sembra.
ma io ho pure calcio a 11
Pure a 11.
Non esageriamo.
esatto, vabbè.
Cioè io già calcio a 5 ore, l'orecchio c'è.
Il canale si può organizzare.
Dai, facciamo.
Anche così uno si
tanto
conosce.
Senti, me lo faccio il gruppo. Il tuo numero ce l'ho, mi sa di sì. Intanto mettilo. Così organizziamo, raga, che domani. O domani o sabato.
sabato
No, io sono
Qual è il cognome?
la settimana prossima.
Nori.
formalmente una esperienza chi l'avrebbe detto
Devo firmare la strada.
Che ti voglio tornare a Napoli.
perché fa caldissimo
Vabbè, alla fine Napoli.
è uno di due non possiede
Raga, datemi i numeri.
Sono stato a marzo la prima volta e mi è piaciuto tantissimo, però un giorno. Quindi vorrei fare.
salvo direttamente.
Poi fino a quando il tempo lo permette.
Marco Luis.
Metti quello il cognome.
Oddio, perché c'è la...
Poi non
Che tastiera è? Spagnola?
Io ci andai il giorno dopo.
348, no?
io prima
Oh, Napoli è bellissimo. Io i primi anni non lo pensavo.
non mi ricordo c'è un giocatore che aveva 17 anni
Il problema sai qual è? I napoletani.
di consegno quello è stato il più forte che ho mai visto.
No, fortunatamente io capito, non sono in quella fascia di napoletani che rompono le palle, però è vero, cioè, effettivamente il problema di Napoli
Io ricordo
vedi su TikTok.
Già ce l'avevo.
Vabbè, quelli che. Però a me il napoletano mi piace. Mi cuore.
Fla, dammi il tuo numero.
già t'ho dato ieri io
Me l'hai dato? Ah, scusa. No, non l'ho creato ancora. No, figura.
lui avrà abbastanza è nato poi dal stadio
Ma mo è enorme, quindi non gli posso anche dire
l'hanno mandato in
niente.
prestito
Tu ce l'hai?
si è fatto là
Cosa? Certo che ce l'ho il tuo. Allora, mo creiamo un gruppetto, va.
e stavo pure l'anno scorso era venuto in Puglia
È una cosa che non voglio fare.
Ah, il memories.
è bruciato
Minchia, valla a
e sa dire
capire.
quello mi dispiace perché lui è uno di quelli che di tutti quelli che ho visto è uno degli unici che è arrivato però si è bruciato così la carriera a 20 anni il nome dell'altra persona 2 anni fermo a quest'età è finito
Tu sei l'unico che mi riconosco. Perché poi io c'ho pure quelli della triennale. Alla differenza, cazzo.
Bocca al lupo,
E nessuno perché lui si è laureato 2 anni fa.
ho fatto quello
vedi un momento si è salvato tipo.
sì così speculato
C'è un qualcosa.
mo sta andando di questa 11
Cercalo, cercalo. C'è Marco, si
O già.
no, sai silenzio
Mi sa Giacomo, vedi la fotoprofilo?
Giacomo,
Conosco uno.
Male, cioè danno in corso di studio che la promozione.
Vedi giù, vedi giù.
Sì,
Sì,
allora.
sì, quanto sei notte, porco.
Te ne vai?
Vale quinto liceo, mo tutto bene.
Vuoi che ti mando la registrazione?
Ma ti posso dire, guarda, in realtà queste cose mezzo le so, poi... Promozione, sono proprio la intro che lei però che non c'è, sto a fare la prima.
Okay, so okay, so we can start this second part, and we have now all the definitions for starting to work with our main object up to now. This is a very important class of problems in applied mathematics that you can find in many situations, but it's important to look at this problem a bit closer. So we look at how to solve this problem, and this will help us in introducing many other instruments from a mathematical point of view. Well, I'm thinking essentially to this problem. We will study the general property of these systems, general properties of linear systems, and then we specialize this structure to a particular case, which is the homogeneous case, and from that case we will introduce eigenvalues and eigenvectors, which are a very important mathematical object, useful that are very useful in many situations. Okay, but in order to do this, in order to introduce eigenvalues and eigenvectors, we have to say what is an homogeneous system, which is a particular case of the equations 1. Okay. So, what is a linear system? So, written explicitly, a linear system, is a system of m equations and n unknowns. Okay, m equations and m unknowns. Consider that the linear system is written in what is sometimes called in a canonical form, just in the way you see on the slides. So one typical trick which is typically used in some exam is to write, for example, the system by exchanging the order of the unknowns between the equations, and this will cause, of course, an error in the solution, and well, it's a very it's a way to let the exam go bad for some students. Okay, so what I'm saying that this is the standard form in which you find the linear system. So this is the canonical form. This means that you have m equations, okay, and the unknowns are the values x. The symbol x are the unknowns, and the unknowns are ordered in the same way for every equation. Okay, so the first place is x1 with its coefficient, the second position is x2, with its coefficient, and then x3, xn, up to xn. Okay, and the same order must be followed in the second equation, in the third equation, and the final equation. So, having written the system of equation in this canonical form, we can try. This is a very detailed description of the system, but sometimes it's not so useful, and well, no, it's useful, but it's difficult to write. So the idea is to express this system in a matrix form, which is a more compact notation. Okay. So all the effort that we have done up to now to define matrices and the operation on matrices can be seen as a way to write the system 1 in a very compact way. Okay? Okay. So the idea is to extract from this system. So the main object is a linear system of equation, but we extract 3 objects. One matrix, the matrix of coefficients. Okay, so the matrix A, typically is A. So it's the matrix in which we collect all the coefficients of the unknown. The rule is that every row, the rows of the matrix are the coefficient, ordered coefficient in order of for the unknown, for the corresponding equation. So in the first row of the matrix, there are the coefficient of the unknown of the first equation. In the second row of the matrix, there are the coefficient of the second equation. Okay? The other thing that you may notice is that the first column of the matrix A are the coefficient related to the unknown x1, to the first, in this case, the first unknown. The unknown, call it x1. The second column of the matrix are the coefficient of the second unknown, of the unknown x2. Okay? You can interpret the matrix in this way. The rows are the coefficient of the unknowns related to a given equation. The columns are the coefficient of a given unknown. Okay? You have these 2 ways of looking at the matrix A. Then, on the right-hand side of the equality, you have some numbers which are not unknown, does not depend on the unknowns. Okay? So, they are numbers. And we collect all these numbers in a vector B, column vector, and then we collect, we define a vector X, boldface X, which is the vectors, the column vectors with all the unknowns. So you can immediately notice that the matrix A is a matrix with m rows and n columns. The vector B has m entries, so it's a column vector with dimension m. M is the number of equations. And the vector X is a column vector with n components. N is the number of unknowns. Okay? Okay. So, given this, we can express the system 1, which is fully expressed by the set of equations, in a very compact way, using the matrix notation. So, this equation, the equation 2, is the matrix representation of the system 1, the previous one. Okay? So you see that this is much more compact notation. Why this is true? Okay, we have defined the row by columns matrix multiplication exactly for this reason. Okay, so look at I have to multiply the matrix A with the vector X. Okay, so by using the matrix row by column multiplication, this matrix multiplication is the first row multiplied by the column. So this means that A11 is multiplied by x1, A12 is multiplied by x2, A1n is multiplied by xn, and then I sum. What I get exactly? The left hand side of the first equation. And this must be equal to B1. Equal to B1. Okay? Second row multiplied by x. Okay? By the vector x. So the second row is A21 times x1 plus A22 times x2 plus A2n times xn. This is the row by column multiplication. Which is this product? Exactly the left hand side of the second equation. Okay? And this must be equal to B2, the second element, and so on and so forth. So we can compactly represent a linear system as by using the row by column matrix in matrix notation, by using the row by column multiplication. So this is very compact notation. Okay. What does it mean to find a solution of this system? Okay. Let's come back to the version 1. What does it mean? Finding a solution of this system, if a solution exists, and now we will see a condition for the existence for the solution, means that I would like to find a vector of unknowns, the vector x, so some values for x1, x2, xn, in such a way all the linear equations are satisfied. Okay, so the value x1, x2, xn inserted in all the equations must satisfy all the equations simultaneously. Okay. This means solution of the system 1 or the same. 2 is not a different system. 2 is only a different way of denoting or representing the system, but it's the same system. Okay? And we may notice that the fact that the system has or not a solution, so a value of x such that all the equations are simultaneously satisfied, depends on what? Well, on the matrix A and on the vector B. No other things. So the system the solution of the system depends on the matrix A, so the matrix of coefficient, and on the vector B. Okay? So the properties of the matrix X and the vector B will determine the existence or not of the solution of this kind of systems. Okay? What can happen? Oh, many things. I would like to, before introducing the main result, which is a theorem that we will not prove, but just it's quite easy to remember the result of this theorem. It's quite easy. But we will not look at the proof. I would like to show you 3 different situations that can happen in a very special case. When I try to do some graphs and pictures, I'm trying to switch to a geometrical interpretation. Okay, just as for the vectors which can be drawn on a plan or in a given space, the linear system has a geometrical interpretation. Okay, And the easiest situation is a linear system with two unknowns. Okay? The case of two unknowns. Suppose that you have a system like this one, A11 x1 plus A12 x2 equal to B1, and then A21 x1 plus A22 x2 equal to B2. This is a special system with two unknowns and two equations. The simplest case that, well, it's not really the simplest, but one of the simplest case you can write. So, a geometrical intuition. What is an equation like this one? Which is the geometrical interpretation of an equation like this one? You know what is this? What is the geometrical object which is described by this kind of equation? Geometrical object means a set of points, x1, x2 on the plan, which satisfies that condition. Okay? You know what is? A straight line. Okay? Recall that maybe you remind the equation of a straight line in a slightly different form, but I'll show you in a moment that these are the same. Okay? Y is ax plus b. What is this? This is a line, right? You know that this is a line? Oh, okay. Let us. This is the first ingredient. Don't think about this one. Forget for a moment for this one. Let us look at this one. This is important. Well, it's a very basic geometry, okay? But it's really important in many situations. So let us look at this object, okay? So this is the x-axis, this is the y-axis. This is the equation which is satisfied by all the points lying on a line. Okay, so this equation, okay, if you look at this as an equation, corresponds to this geometrical object. Okay, so what does it mean? This means that all the points x and y, so which are having the coordinate x and y, which satisfy this relation, lies on this line. Okay? Okay, from this representation you may see what is the effect. Well, this is nothing to do with the linear system, but it's important to be able to manage this object. What is the effect of changing b in that equation? So x and y are the coordinate of the points in the plan. And so x and y, if they satisfy that relationship, lie on the line. Okay? They lie on the line. Okay? All the points in the line satisfy the equation written there. This is the Cartesian equation for a straight line in the plan. Okay? Okay, what is the effect of B? Well, the effect of B is to switch, to change the to a parallel movement of the line. Okay? Of course, given this equation, you can compute a lot of things. For example, the intersection with the axis, but these are very intuitive things that I'm trying to. I want to imagine that you already know all these things, so that you are able to find, for example, the intersection with the axis and these kind of things. Okay. So B is related to a parallel movement of the straight line. If you change B, you take another line which is parallel to the first one. Okay? And what is the effect of changing A? The slope. So A is the slope. Okay? So if A is 0, you get a line which is parallel to the x-axis. Okay? So it's a flat line. If A is 1, for example, you take something which is in the middle of the first quadrant. Okay? Okay. So this is the Cartesian representation of a line, a straight line. Let us take a bit of algebra, okay, modification of the equation, but we may write this same equation, so y equal to ax plus b, we may write this as ax minus y equal to b. Okay? Oh. Okay, I'm just changing the position. Okay, so ax minus y equal to minus b. Okay? It's the same. Okay? Yes. Okay? This is the same. But this has the same structure of this one. Okay? x1, x2 are the two coordinates. Okay? The unknowns, and these are the coefficients, a1, 1, a1, 2 equal to b. So, as the same structure of this one. Okay? Let me, if you want to be, we can write the same system in this way. Let us change the name of the unknowns. I used x1 and x2 just to be coherent with the slides, but we can write in the same way. This is the same system. I only changed the name of the unknowns, but the name are names, so I can call y instead of x2 is the same. Okay? So you may see that this equation has the same structure of this one. So this is a line in the plan, and this is another line in the plan, since the coefficients are different. Okay? So what does it mean? What is the conclusion of this reasoning? So let us take the system. I write again the system. a11x plus a12y equal to b1, a12x plus a22y equal to b2. This is the linear system. Two equations in two unknowns. Okay, so the two equations can be represented as a straight line on the plan. Okay, this is the x-axis, this is the y-axis. So the first equation is this straight line. Okay? So the second equation is another straight line. So what does it mean to find a solution for both the equations? Well, geometrically means to find the intersection for these two lines. Suppose that this is this straight line, then we have this is the second, this is a straight, oh my god, this is not straight. Okay, this is another straight line. You understand this point? The red one is this equation, the black one is this equation. So these are the geometrical representation of these two equations. So every equation is represent a straight line in the plan. Okay? Okay, so what does it mean, the solution? Well, it means that we are looking at the intersection. Why? Well, this point, if it exists, which is in the intersection, is a solution of the first equation, since it lies on the black line, but is always even a solution of the second equation, since it lies on the red line. So it's a solution of the system. Okay? So this is the geometrical interpretation for this very simple system of equations. Two lines in a plan. Every line is an equation. The plan means that we have two coordinates, so there are two unknowns. Okay. What can happen in general? And this depends on the coefficient A1, A1, 2, A2, 1. This is A2, 1, 2, 1. This is an error. This is 2, 1. Okay. What can happen if I change the coefficient A1, 1, A1, 2, A2, 1, A2, 2, and B1 and B2? What can happen? Well, there can happen essentially three situations in this case. The first situation is this one. And this means that we have a unique solution, the intersection between these two lines. Another situation that can happen, in this case, geometrically, that you can imagine that this is the first equation and this is the second equation. Two parallel lines. There exist solutions? No. The system has no solution. So one solution, no solution. Okay, but can happen another situation. These are parallel lines. Another situation that can happen is the following. I have this first line, and then I have the same line written in a different way. Okay. The two equations, even if they are written in a different way, represent the same line. So how many solutions there are? Infinite solutions. Okay, so we may see immediately with a geometrical intuition that a simple linear system with two equations and two unknowns may have one unique solution, no solution, infinite solutions. Okay? How can we decide which kind of solutions, what is the structure of solution for linear systems? For this linear system? Yes. I will now introduce a result which characterize this kind of situation in general for any kind of linear system of any dimension. Okay? So a very general result, very general. And the result, of course, for this case, 2 by 2 is not necessary to go to the theorem that I'm showing you now. It's sufficient to do the calculation by pen and paper. You take the system, you solve it, and you see what happens. This is possible. In this case, it's quite easy. Okay? But in general, this is just to show you the situation, just to convince you that the theorem is important. Okay? What is the theorem? So the theorem is called the Rouchet-Capelli theorem. Rouchet-Capelli, I discovered that it's not universally known as Rouchet-Capelli. Some books and some texts from other areas that is not known as Rouchet-Capelli. But anyway, the result, even if the name is different, is always the same. This is the beauty of mathematics. Okay, so in order to apply this Rouchet-Cavalli of this theorem, we have to build, so given a linear system, we have the matrix of coefficient and the vector B. These are the two objects that we consider. Then we, with these two objects, the matrix A and the vector B, we built an augmented matrix. So we have the matrix A and the matrix A in which we add the column B. Okay? So just two objects, the matrix A and the augmented matrix A and B. Okay? Then the Rouchet-Cavalli theorem says that the system AX equal to B admit solutions if and only if the rank of the matrix A is equal to the rank of the augmented matrix A and B. No more. Okay? So a very simple conditions in which we have to compute the rank of two matrices and compare this rank. If the two ranks are equal, then the system has solution. If the rank is different, the system has no solutions. Okay? This is the first part of the theorem. Another way of saying this, the system has a solution or the system is consistent. Another way of expressing this, the same condition. Okay? The second part, and this is the first part of the theorem. Notice that this is an if and only if. If and only if means that the two sentences are essentially the same. If the rank is the same, then the system admits a solution. If the system admits a solution, then the rank is the same. Okay? So the two conditions are equivalent. The system admits a solution, the rank of A and the rank of the augmented is equal. These two conditions are equivalent. Okay? Then, second part of the system, of the theorem. Second part. The first part is what in mathematics is typically called a existence theorem. So the theorem says only if the solutions, a solution or more than one solution, exist or not. What are the solutions? Well, this is another story, completely another story. So this is an existence theorem. Okay? Second part of the theorem says something more, not much more, but something more, about the number of solutions. Think always to the previous case with the straight line. One solution, no solution, infinite solutions. Okay? So, this is a notation for which remind us how many solutions can have this system. Okay, and so the notation is just a symbol, just a notation. Okay? The notation that we use is this one, is infinite to the power of n, which is the number of unknowns, minus the common rank of the matrix A and the augmented matrix. So if the system is consistent, so if the rank of A is equal to the rank of the augmented matrix, the number of solutions, so the system has a solution, then the number of this solution has this dimensionality. So it's infinite to the power of n minus the rank. What does it mean? So essentially it means that the solution can be unique one vector, or the solution can be infinite. Think about the straight lines, okay? But what does it mean, infinite? The meaning of that symbol, I want to stress that it's just a symbol. We can say the same thing in a different way. Maybe, for example, explicitly. It's just a symbol to remind what is written explicitly here. Okay? But the situation is the following. So if the rank, look at what happened here, if the rank is equal to n, okay, which is the number of unknowns, okay, the number of unknowns is the number of the columns of the matrix A, okay, the number of unknowns. If the rank is equal to the number of the unknowns, then n minus the rank is 0. Okay? N minus the rank is 0. So this symbol reads as the infinite to the 0. And you know that in mathematics, when you take the power 0, the result is 1. Even if this is an infinite, but it's just a symbol to remember what happens. Nothing to do with limits and these rules, complex rules in calculus. Nothing to do with this. It's just a symbol to have in mind what happens immediately. Okay? So I look at n minus the rank. If n minus the rank is 0, so the rank is equal to n, then we have a unique solution. This comes to the notation infinite to the 0. But I want to stress, nothing to do with limits. Limits that something going to infinite. No, nothing to do. It's just some notation, a special notation. When the rank is equal to n minus 1, this means that this exponent is equal to 1. Okay? And the exponent equal to 1 means that we have infinite to the power of 1 solutions. So this means that the set of solution has an infinity of solution which more or less are spanning a straight line. Think about the picture that the case of the simplest case, the simple case of the two equations in two unknowns. Okay, the case that I draw in the whiteboard. Okay, think about what happens. So suppose that in that case n is equal to 2. We have two equations, it's two unknown, the unknown are 2. So n is the number of unknowns, so is equal to 2. Okay. Suppose that the rank, the common rank of the matrix A and the augmented matrix is 1. Okay? And not is 1. So we have the exponent 2 minus 1. This is exactly the case, can be proven that is the case in which the two lines are the same line. So we have the infinite set of solutions. Okay? If the rank of the matrix and the augmented matrix is 2, in the previous case, then we have infinite to the 0 solution. So is the case in which the two lines intersect in a unique point. The other case, when the two lines are parallel, corresponds to the case in which the rank of the augmented matrix is 1, and the other is 2, and the rank of the matrix A is 1. Okay? And we have no solutions. Okay? So, just to think about the example of the two lines. The case in which the two ranks are different is the case of parallel lines. That's the case of different rank. If the ranks are equal, so the solution exists, then we may have two possible situations. One in which we have a unique solution. This is the case in which the rank is 2. The other one is the case in which the rank, the common rank is 1, and so we have an infinite, to the power of 1, set of solutions, which means that the solutions are on the straight line. Okay? This is the translation of the algebraic condition. This is a completely algebraic condition to a geometrical interpretation. Okay? Of course, if the rank is n minus 2, the system has infinite to the power of 2 solutions. This means that there are 2 free parameters to describe all the possible solutions. This is the case when you intersect some plants, for example, instead of straight lines. Okay, okay, just a final just a final corollary, which specializes the Rouchet-Capelli theorem to the case of a square matrix. What happens when the matrix is a square? Oh, I didn't stress enough that the Rouchet-Capelli theorem is general, so it may be applied to every matrix, to every linear system. M equations, N unknowns, N can be whatever you want. Okay? What happens when n is equal to n? So for the special case of square matrices, so systems in which the number of equations is equal to the number of solutions, well, it can be proven, is a consequence of the theorem, is that the system, the square system, has a unique solution if and only if the determinant of the matrix A is different from 0. Why this is true? Well, essentially for 2 reasons. I give you a proof of this just by looking at these slides, these notes. So what happens if the determinant is different from 0? It means that the matrix A has maximum rank. Okay, so the rank is n. The matrix is dimension n, so the rank is n, maximum rank. The determinant is different. So, imagine this. You have the matrix A, which has maximum rank, n. Then you look at the rank of the augmented matrix. So this is the matrix A, and then you add the vector B. Okay? So you get a matrix which has n rows and n plus 1 columns. Okay? So you are adding a column, n plus 1. But the rank can be n plus 1? No. Since the rank is the smallest dimension of the matrix. So if you add the vector B to the matrix A, the rank is always n. It doesn't change. It cannot change. Since the rank is the smallest, can be at most the smallest dimension of the matrix. So if the rank of A is n, then if you add some columns, the rank is n as well. Okay? It cannot change. And so the rank of the 2 matrices, the matrix A and the augmented matrix, is equal. And so you have a solution. And the solution is unique since n is equal to the rank. Okay? So, in the square case, the square linear system, square means that is related to the matrix n by n, okay, square matrix. The linear system has a unique solution just by looking at the determinant. If the determinant is different from 0, the system has a solution. If the determinant is equal to 0, then the solution is there not exists a unique solution. Okay? So the unique solution is when the determinant is different from 0. And this is the most important condition for linear systems. Okay? Okay, so we can stop here. Next lecture is for you is Friday, and you will have the practical lecture.